All right, so welcome to the first video lecture for chapter 5. I think it's 5. I think we're on 5. And the focus for today will be friction. So this is a really fun lecture. The problems are really fun. So feel free to watch this many times because there's probably a lot of information here that you won't get the first time. So uh, we'll first start with static friction. So I've talked a bit about, ultimately what's happened with static friction. But the thing that's important about static friction is you have two objects that are in contact. That means there's some sort of normal force that's exerted between them. And because of that, there is sort of an inherent uh, resistive force that acts on objects. So if they don't move relative to each other, but they would, if there were no friction, we of course call that static friction. And static friction is always going to be perpendicular to the normal force. Or in other words, it's always going to be perpendicular to the surface. So it's going to be in the direction of motion or the direction that the motion would take place. So, I mean, if you could look microscopically, like you see the picture on the right here, what's happening is that surfaces are not entirely smooth. And so because they're not entirely smooth, there is a certain amount of force that's required to sort of overcome a lot of those little contact points there. So static friction is happening because the two surfaces are not able to overcome those rough surfaces they have there. But once you can do that, then it becomes much more easier to move the object, even though there's still friction. All right, so let's start looking at what's going on here. So we have a box on a rough surface. It's pulled by a horizontal rope with tension T. The box is not moving. Okay, so think about what forces act on this thing, right? So if you think about it, obviously there's tension to the right, and there's normal force going upward, and there's gravity going down. Now, if that was the only three forces that are acting on this object, then it would be accelerating to the right. But the situation tells us that the box is not moving. So what does that imply? Okay, so think about that for a moment, and the answer here is B. So static friction is equal to the tension. Those are the forces in the x direction. And because they're equal, there is no net force in the x direction. Therefore, there's no acceleration. And if the object wasn't moved to begin with, it won't continue to move. And so what's important about this question here is this. Static friction, okay, has a magnitude that is equal to whatever it needs to be, okay? So, and that can vary because, for example, if this tension, if it's say you're 5 newtons to the right and it's not moving, well, then static friction is five newtons. Well, what if I up the tension to 10 newtons? Well, if the box still doesn't move, then the static friction has to be 10 newtons. So, static friction's value is always whatever it needs to be static friction, right? Okay, so this figure here shows a person that's pushing on a box. The box is not moving. They seem to be very upset at this box for some reason, and they want to push it over, but they can't do it because the static friction is just too large, and their push and the value of static friction are equal to each other here. Okay, and so static friction is going to be pushing to the left. That is opposing the start of motion, right? So the motion would be to the right, but it's opposing that. All right, so what we're seeing here is that static friction is whatever it needs to be, right? So you got to push, and the box doesn't move. Static friction is equal to that push. Push a little harder, static friction is a little bit bigger. But then there's a maximum, okay? And we call this F, well, I label it F sub S max. This is the maximum value of static friction. At some point, this person, right, can push this box so much that it will eventually start moving. So there is a maximum static friction, okay? Maximum to it. And then after you overcome that, it switches to kinetic friction. Okay, so the maximum possible value that you can have for static friction has a very sort of clear quantitative form, okay? And it's what you see here. It's mu sub s, Okay, mu is called a coefficient of static friction, and the n here is the normal force. Okay, so there's two parts to this. The maximum static friction that can happen between two surfaces depends on a constant, which is mu sub s. Now, mu sub s is a material-dependent quantity. It's not something you ever can figure out on your own. These are all things you look up in a table. So I have a table here in a moment where you can look up sort of standard ones. But if you have like concrete on concrete, there's a coefficient of friction for that. If you have rubber on concrete, if you have ice on ice on ice or things like that, just wood and ice or something like that. So you have to sort of know what the surfaces are. So your textbook has a table like this, and I'll provide a table here. But if you think that static friction is a possibility in your problem, you have to be mindful of the materials. So when you read a problem, and if it says the word concrete, if it says the word steel, if it says wood or something like that, that is something that you want to take note of and realize that you may have to be using a coefficient of friction for that. All right, so that's a material-dependent quantity. The other part is the normal force, right? So you got to know what kind of supportive force there is on the object, and those are the two things that matter. So what happens is if you push on an object and it doesn't move, that means your static friction is under the maximum, okay? You can increase it, and then when it starts to move, we say that the object slips, okay? And that's when you've reached the maximum static frictional force. Anything larger than that would not be a static frictional force because you would be able to overcome static friction and you'd be able to convert it into kinetic friction. Okay. So, got a box here with a weight of 100 newtons, is at rest, then it's pulled by a 30 newton force. Does the box move? All right. Okay, so like you do with every problem that we ever look at, is you ask yourself what forces are acting on the object. Gravity down, normal force up. We have a 30 newton force to the right. The box is at rest. Will it move? There's going to be a kinetic or static friction to the left. How do you determine that? Well, you have to determine if 30 newtons is above the max static friction, right? And so the way we figure that out is we take the coefficient of static friction, which is in this case 0.4. We multiply it by our normal force. Now, normal force here would be equal to gravity. So it's 100 newton weight. So 0.4 times 100 is 40 newtons. You need to push this box. Oh, I guess you need to answer. Okay, so the answer to the question is no. Okay, so you need 40 newtons. If you're under 40 newtons, the box doesn't move. When you hit 40 newtons, though, what happens is the box slips and it starts to move, and you no longer have a static frictional force. You have a kinetic frictional force, which we will deal with a bit later on in the lecture. Okay, great. Oh, look, we're dealing with that right now. Okay. So the next friction that we're going to consider is the kinetic friction, and that is if the two surfaces do move relative to each other. In the example here, we have a box that's being pushed. Now, this person's really mad now because they're pushing the box and it's starting to move, so now they're really showing it. And it's accelerating, all right? So that means the push is bigger than the kinetic frictional force. And if you look here, the kinetic frictional force has a very similar expression. It's mu sub k this time in n. Now, mu sub k is, again, a coefficient of kinetic friction. And again, material-dependent thing. You have to look up a table. You have to know the surfaces involved, what the materials are, and then you look up a table to see what that value is. Now, here's the nature of this stuff, though, is the kinetic coefficient of friction is always less than the static. And what that means conceptually is this. It is harder to start motion than to maintain it, okay? So like if we look at the example back here, if we reach that 20 Newton force, okay, 40. If we reach that 40 Newton force, then the box slips and it starts to move. And then the friction switches to kinetic and the coefficient is not 0.4 now, it's 0.2 now. So that means the kinetic frictional force has dropped down to 20 newtons. Now, if we're pushing with 40, the kinetic friction is only 20. F net's not 0 now, and this box not only will move, but it will accelerate. And if you want it to stay at a constant speed, you're going to have to lower your push down. All right, great. All right, so question for you now. Tension to the right, Pull in the box, okay? Tension is bigger, okay, than the kinetic friction. So that means the box is speeding up. All right, the rope breaks though. So what I mean by that, if the rope breaks, the tension disappears. And we want to know what will happen to the box. All right, so think about this for a moment. And the answer is D. All right, so what happens here? Let's look at it. Free body diagram while there's tension, right? Gravity down, normal force up. Tension to the right, kinetic friction to the left. Okay, so the tension disappears. All right, if the tension disappears, the kinetic friction is still there. And that will cause the box to experience an acceleration that is opposite its direction of motion, which means it will slow down, and it will slow until it comes to a stop. All right, so let's look at the other options, though, because it's actually really helpful to look at the other options and to know why they're wrong. In fact, I like that better. I like trying to figure out the reason why the three things are wrong rather than why the one thing is right. Okay, stops immediately. Okay, well, that's kind of a terrible thing. What does immediately mean? I mean, immediately, I guess, means delta t equals 0, which doesn't really ever happen, but it doesn't stop immediately because there has to be an amount of time for a force to produce the acceleration to bring the velocity down. You just got to go back to the kinematic equations, and once you know the magnitude of the acceleration, well, then you figure out how long it takes. Okay, so that's just totally wrong. Continue speeding up for a while, for a short while, and then slow. Okay, B does not work at all because the reason it speeds up is because there is some net force to the right. Well, the tension disappears. There's no longer net force to the right. It can't continue to speed up. It's impossible. All right. Keeps its speed for a short while and slows and stops. Well, that's just the dumbest option. Keeps its speed for a short while. Because if you keep its speed, that means it's constant speed. That means you're going to have a balance of forces in the x direction. Well, it's not like the tension gradually goes away. I mean, when the rope breaks, it's just gone. Right? So C is terrible. All right, D is right. Great. Let's move on. Ooh, okay. So we got this box now, moving to the right. The tension is up at an angle. So the box is being pulled to the right at a steady speed. Okay, steady means constant velocity, right? And the tension angles upward. All right, so what's going on here with the normal force? Because here's the thing. We need to figure out the normal force before we consider what's going on with friction. Because both the static and the kinetic friction depend on normal force. So when you solve your problems, you have to know what the normal force is first. All right, so what's going on here? Think about this for a minute. The answer is C. All right, so in this situation, now this is why I don't like the word weight. You see in a lot of books, and maybe if you're looking at things online, a lot of people use the word weight and they mean mg. And that's not right. It's not right. Okay, so in this case here, we have to think about the free body diagram. Okay, so we got gravity down, normal force up, tension's up at this angle here, and there's got to be obviously some force to the left here that balances tension so that we can do our steady speed here. Okay, so the force that's to the left is some kind of kinetic friction, and it matches the horizontal component of the tension. Now, if you look here, though, at the forces in the y direction, what do you got? You got gravity down, you got normal force up, and you have a component of tension that's up. Okay, a component of tension that's up. What does that do? That's in the same direction as the normal force. So that tension is doing some of the work of the normal force. Right? It's basically lessening the load. When you are tugging with the rope that way, you are pulling to the right, but you're alleviating some of the normal force. You're helping to support the object. So what happens is normal force drops here. So if you're pulling on this object and the normal force is a little bit lower, that means your frictional forces are different now. Okay, so in a situation where you have, only gravity and normal force in the y direction, then normal force equals mg. But if there's any other forces in the y direction, that is not the case now. Okay, so this is a very common mistake that students make. in so many situations they say, well, normal force is equal to gravity, right? And that's true in a lot of cases, but there's a lot of cases where it's not true. So do not always make that assumption. It's always going to be different. All right. So let's look now. Let's actually put some numbers behind things here. We got a box being pulled to the right by a rope that angles upward. It's accelerating. Find the acceleration given in terms of the variables. Okay, so you're not going to like this problem. But I love these problems, and if I could, assign more of these, I would. I don't like problems with numbers. There's no numbers here. I love that. All right. Now, there is friction. It's not stated in the problem, but if you look at the picture, it's a mu sub k there. So there's definitely a friction we need to consider here. All right, so let's look at how we analyze this. All right, start with the free body diagram, right? Free body diagram has gravity down, right? We have normal force up. We have our tension at an angle. We have our kinetic frictional force to the left. Okay. Now that's it. That's four forces. That's all we have here. You can, again, if you're not clear about that, do your force identification diagram. We only have one point of contact here, and that's the floor. Well, actually, we have two, right? The floor and a rope or a rope. Okay, so there's 2 points of contact: rope, floor. The floor does two forces, one in each direction, and then obviously the tension is the one for the rope. All right, now we write out Newton's second law. So the summation of forces in the y direction, we have our normal force up. We have tension, a component of tension that's upward. Okay, so I have a t sine theta there, and we got minus Fg, which is the gravitational force downward, and that's set equal to 0 because there is no acceleration in the y direction. We go to the x equation now. We got t cosine theta. That's the force. That's the component of tension to the right. And it's being opposed by kinetic friction. We are told that we're accelerating, so we will set that equal to m a sub x, okay, which is the acceleration in the x direction. All right, good. So we want to solve for n, all right? The reason why we solve for n is because we're going to need that in the kinetic frictional term here. And so you're going to start to see a pattern in these problems now. From here on out, you're going to start to see a pattern where the y equation establishes our normal force and the x equation establishes the friction, but it needs you need the normal force to do that, right? So, okay, so we solve for normal force in the y equation. You can see it's mg minus t sine theta. And that equation makes so much sense, right? Because what is normal force? It's gravity minus the support of the rope. Okay, if there was no rope here, normal force would be equal to gravity. But having the minus t sine theta here is indicating that the tension is supporting the weight. Okay, the weight when you're at rest, I should say. All right, so then we go to the x equation, right? Go to the x equation, and we got t cosine theta. The f sub k, we turn it into the numerical form of it, so that's mu sub k times n. I just inserted what n is here, mg t sine theta, and that equals ma. And so what we want to do here is we want to solve for the acceleration. So we would just divide the whole equation by m, right? And so when we look at this equation, that's why I like not having numbers, because you can look at all the variables that matter. All of these variables matter, right? If you want to know why the object accelerates and the rate at which it accelerates, this equation is telling you all the things that matter, okay? The amount of tension matters. The angle of the rope matters, right? The weight of the object when it's at rest matters, okay? The surfaces matter because you have that mu sub k. So when we read this, what do we see? We see, well, t cosine theta here, right? What is that? That's the force that's pushing it to the right. Okay, well, it's being modified by friction, minus friction, all right? And so we have friction here, and if we even look in the normal force, the normal force is modified by the tension. So the tension plays two roles here, right? The tension is pulling it to the right, and it's lessening the amount of friction, right? And then obviously we divide by mass because that's part of Newton's second law. So great problem, fantastic problem. If you have any questions about this, this is like really key. You really want to understand what's going on here. If it's not clear, I'm going to have a discussion thread in Canvas for this. Email me, talk to other students, watch this video 10 times, print this picture out and frame it in your room so you can always watch it, and you can, just maybe if you stare at it for long enough, it just makes all sense. But whatever you need to do, because this is so crucial, if you get this, you'll get a lot of things that we do later. So if you don't get it now, that's fine. You're learning physics, right? I don't expect everybody to learn everything immediately. Why do I have two of these things up? Oh, that's different. Okay. All right, let's move on. Okay, so I have a little minor topic I have to talk about. It's kind of a nasty thing that I have to mention, but all right, so there's kinetic and static. There's also a rolling friction. Okay, rolling friction, right? And it's not something that we're going to do much with. It's a little complicated, I guess you should say. But it's an inherent friction that happens because of the motion of like a tire rolling. Okay, so here are the different things about tires. I'll just tell you this: if excuse me, if you're skidding on a road, skidding means the tire is not spinning at the rate it normally would. It's to some extent it's being dragged. Like the car is being dragged. That's kinetic friction. Under normal circumstances, though, you have static friction is what propels the car. I mean, what makes the car go forward is the same reason that why people go forward when they walk. You plant your foot on the ground, static friction propels you. Well, okay, it's sitting at the wheel. The surface that touches the ground, right, doesn't move relative to the surface. So you are being propelled by friction, but there's an inherent rolling friction that occurs because the tire isn't perfect. It will deform to some extent. and so there's a rolling friction. So in some situations that we look at, it may be sort of weird, like how is there a friction here? And it's due to rolling motion. So that's all I'm going to say about it. We're not going to do anything more than that. All right. So here are really common coefficients of friction. This is out of a textbook that I used to use like a long time ago. You're welcome to use these values. You're welcome to use the textbook that we have now's values. I don't imagine they're very different. I do not recommend that you attempt to look up values on the internet because all you're going to find is a bunch of engineering geeks that have coefficients of friction for like every possible surface with every possible temperature and atmospheric pressure and all. Just don't look up. Just based on textbook things. Okay. If I know you got a value from a textbook, I'm happy. Okay, so this graph really beautifully illustrates what's going on here, right? So what's being illustrated in the graph is this. Say I have a box. So I'm this person, that I'm very angry with my box and I want to push it over. So what I'm doing is, this graph here is basically the force of the push versus the static friction that's on it, right? So what you see here initially is we have a nice 45-degree line, all right? And so what's meant by that is, the slope is 1. And so as you push the box, the value of your push is going to match what the static friction is. Okay, so we see this graph, start to increase. All right. And so you push and you push and you push, but there is a maximum value, right? At some point, you push hard enough and the box moves. So that means you've pushed hard enough that you have reached the max static frictional value, right? Mu sub s n. So the box slips, it starts to move, and then that static friction immediately switches into kinetic friction, right? Now, the coefficient of kinetic friction, however, is significantly lower than the one for static friction. So if you were to maintain the same push that you did when it started to slip, then you would actually be supplying a larger force than kinetic friction, and you're going to cause your box to accelerate. So what you can do is, if you don't want to do that, say you just want to, make the box just move at a constant speed, you'd have to lower the amount of force until it matches whatever the kinetic friction one would be. So mu sub k times n. And then it goes at a constant speed. Okay. So anything above that would cause it to accelerate. But if you want to, do mu sub k times n, then it's going to move at a constant speed based on whatever, a little part of acceleration you actually did induce on it when you were pushing with the static max. All right. So that's kind of an interesting thing here. So you've experienced this probably. If you ever pushed on a large object, you will notice that it is always harder to get it to start to move than to maintain its motion. And you never need to, when you finally get the object to move, you can lessen the amount of push that you have because you don't need to stay at that static max anymore. All right. Great. All right. So Oh, this is a great problem too. All these are great problems, by the way. All right, we have a 5 kilogram wooden box that sits on a wooden ramp that has its angle of inclination slowly increased. At what angle will the box start to slide down the ramp? Will the box slide down at a constant speed or accelerate? Well, you should already know the answer to the last one, but we'll look at everything here. Okay, so as always, let me make this bigger. There we go. That looks good. All right. Okay, as always, free body diagram. All right, so I have a tilted coordinate system. Right? I guess my ramp goes up and to the right. That's that. I don't know why I did that, but that's why I did. Gravity down, normal force perpendicular to the ramp, and initially static frictions is happening here. Okay, so I'm only drawing one free body diagram right now. Okay, and I'll explain how this looks differently if we have things move. But just imagine that this ramp is very shallow, right? It's very, very shallow. And so what happens is the static friction is not very large because all you need to do here, if your box is not moving, the component of gravity that's down the ramp will have to be equal to the static friction. So if you don't have much of an angle, you don't need much static friction. All right, so with the forces we have here, and there's only 3 of them, we go to Newton's second law. We say, okay, we have summation of forces in the y direction. It's going to be the normal force, which goes upward, minus the component of gravity that is perpendicular to the ramp. So that's an mg cosine theta. We're not accelerating at the moment. Well, we're never going to accelerate in y, so we'll just set that equal to 0. All right, what's going on in x? Static friction. Now, look at my coordinate system here. I put my x on the left. So that means the left is negative. No, the left is positive and the right's negative. Okay, so again, I don't know why I did this, but I did it. All right, so left is negative. Oh my gosh, sorry. Left is positive and right is negative. Okay, so in my equation here, I have my static friction is negative. I decided that right is negative, and I have mg sine theta. That's the component of gravity that is down the ramp. I'm setting that equal to 0 right now because I'm not going to be accelerating at the moment, right? Okay. So normal force, you go to the y equation, normal force is mg cosine theta, right? Static friction is mg sine theta. So that's real nice and simple, right? And so what happens, let's look at these things, right? The static friction is whatever it needs to be, right? And what does it need to be? It needs to be mg sine theta. That's it, okay? Now, what happens is, as you start to up the angle, okay, think about what the sine function does, right? Sine function is initially 0, and then it gradually increases to 1. So that means here that initially your static friction is just fine, but as you up the angle, the sine function value increases, and you will start to creep towards the static max. Okay, what's the static max? Static max is mu sub s times n. So as you increase your angle, not only are you increasing the static frictional force, but you're decreasing your normal force, right? Because the cosine starts at 1 and then it goes down to 0 as you increase the angle. So you got 2 competing factors here, right? You got your static frictional force that will increase as you raise the angle, and then your normal force decreases, so the condition to start motion starts to go down. Well, when does this move? It moves when you've reached the max static frictional value. So I'm going to take my F sub s and I'm going to replace it with mu sub s times n. Now, by the way, I just want to tell you something here. When I change F sub s to mu sub s n, okay, what I'm doing there is I'm doing a check, basically. I'm checking to see when we slip. So there's very few, I don't know, I guess there's no circumstances where you actually need to put in mu sub s n, because the normal force, the static frictional force is never equal normally to mu sub s times n. It's a check. When it reaches the value, things change, though. That's what I mean. I guess it gets there momentarily, but it's always done as a check. Have I reached my max static or not? So in this case, I'm going to change F sub s here to mu sub s n, right? Now, what is n, right? N is mg cosine theta, right? The mg's drop out. I got mu sub s cosine times equals to sine. I'm going to divide by cosine, and I'm going to use a trig identity to say that's tangent. So look at this. This is beautiful, right? The coefficient of static friction is equal to just the tangent of the ramp angle, right? So, okay, so I solve for the angle, and it's the inverse tangent of the coefficient of friction. That's amazing. This applies to any situation, right? If you have an object on a ramp and you increase the ramp, when does it move? Well, it moves when your angle is the arctan of the coefficient of static friction. So 0.5, that's, let's go back to my table here. Where's the table? Let's go back to table. Where's the table? Here it is. Okay, so what I got here for wood on wood, right? Wood on snow. That's strange. Wood on wood is 0.5. Steel higher, rubber and concrete higher. I did just for wood on wood. So if you have a wooden box on a wooden ramp, a 27-degree angle, you have to exceed that, or I guess you have to reach it, and then it slips. So that's not much of an angle, right? Obviously, if your static frictional force is higher, so your static coefficient is higher, like if we did rubber and concrete, that's 1, right? What's the inverse tan of 1? 45 degrees. So if you got a situation of rubber on concrete, which is like, cars on roads, your coefficient of friction is 1, your angle is 45 degrees. So you don't want to make a road has a greater grade than 45 degrees because you're going to get all your cars slipping and falling down the road there. So that doesn't work. Anyway, that's a really great equation. So here's what happens, right? Let's say we do wood on wood here. Oh, we do wood because it says right here, wooden box, wooden ramp. Okay, I didn't pay attention to my own problem here. All right, 0.5 is the static frictional coefficient here. So when we reach 27 degrees, we slip. Under 27, everything's great. When we reach 27 or go any higher than that, then boom, things switch. It becomes kinetic friction. Now the kinetic coefficient of friction is much lower, so that means our force of gravity is already going to be much larger than the kinetic frictional force, and our box accelerates. Okay. And we actually could, you could take this a step further and say, okay, all you do is this. You go into your problem, and every place you see static frictional force, you just change it into a kinetic frictional force. Any mu sub s's changes to mu sub k's, and then you just work out what your acceleration is. So the x equation would change, right? You would put a sub x here. You change your static frictional force to a f sub k. And then down over here, we got our mu sub s's. Those all become mu sub k's. So it's pretty easy. Once you decide that you slip, then everything switches. Okay, where am I now? All right. Oh, this one's a good one too. All right, so we have a 2-kilogram wood block. Slides down a vertical wood wall. So wood on wood, right? You push on it with a 45-degree angle. What magnitude of force should you apply to cause the box to slide down at a constant speed? All right. Well, okay. So let's just think about this for a moment here. What if we didn't have, right, a push? It'll just fall, right? And that means if we have a weak push, it still falls. But at some point, our push could increase, and then the box is stuck because it can't overcome static friction. But then if we really push it, right, then we can overcome static friction, and then the box starts to go upward. So this is an interesting problem, right? But we want to have constant speed. So that means we want to have our Newton's second law equations equal to 0. So let's do that. Well, let's look at what we got here. Okay, as always, let's look at our free body diagram. So we got our free body diagram of the box. We got gravity down, right? Our surface is to the left. That means the normal force is to the right. The push is at a 45-degree angle. It's a second quadrant vector. So that means I'm going to draw it over here, right? 45 degrees. And then now, here's the thing. If the box is moving down at a constant speed, that means we are not dealing with static friction. We are dealing with kinetic friction. The box is moving, okay? And if the box moves down, the kinetic friction needs to be upward then. So these are our 4 forces. We write out Newton's second law in the x direction. Normal force is to the right. I call that positive. The push is a component to the left, and I multiply that by the cosine 45 to get the component in the x direction. Great. I said equal to 0. We're not accelerating in the x direction. Let's go to the y component. We got our kinetic frictional force upward. We have a component of our push upward. So I have a sine 45 here to give that component. Then we got gravity down, that's mg, and that equals 0. So I solve for my normal force, it's push cosine 45. I plug that into the y equation, right? So this F sub k now becomes mu sub k times n. I put in what n is, right? And then what am I solving for? I'm solving for the push, right? So I factor out the push here. I have two terms with F push. I factor it out. If I factor that out, I have a mu sub k cosine 45 plus sine 45, so I divide by that. So mg divided by that is my expression for the push, and I put my numbers in and I get 23 newtons. So if I push with 23 newtons, okay. Now, do realize there is one thing kind of missing here. This assumes that we have already overcome static friction. Okay, so what probably will happen here is this, is that I won't push the box too much right now. Okay, you can actually work this out for like, for a 23 Newton force, you can switch everything to the static friction. And you can ask yourself, well, is 23 Newtons enough to even get it to move? I don't know, probably not. Okay, but I'm making an assumption here is we've lessened our push to the extent that the box does start to move, and then I adjust my force to give it a constant speed. Okay, so just realize that. But you can always check that for yourself by just switching all the mu sub k's to mu sub s's and do that. Anyway, so what are we saying here down here with the force of the push? Well, it's basically gravity modified by, right, by a normal force, right? And then the sine 45 comes from the component that's trying to make the box move upward. It's not moving upward, but the combination of the stuff down here is what's modifying that push there. So anyway, we get 23 newtons out of this, and that's what's required for a constant speed. So great problem, right? It's a weird problem, though, because normal force is, it's horizontal now, and the push is, but really think about what the push does here, right? I mean, like, different pushes do different things here. This box could either be accelerating downward, it could be moving down at a constant speed, it could be moving up at a constant speed too, by the way. It could absolutely be moving up at a constant speed here. You have to just maintain the same situation, right? In fact, when you look at this, right, moving downward, the only thing that would be different if we moved upward is you'd switch the kinetic friction direction. So then your push up is all that's going upward. So if you manage to make it slide upward at a constant speed, you just switch kinetic friction. All right, let's move on. Okay, one last example. This one's a doozy. This one's complicated, I guess, sort of. Two packages at UPS start sliding down a 20-degree ramp shown. Package A has a mass of 5 kilograms and has coefficient of friction, that should say kinetic. This stuff is moving. Well, I guess it's implied. Okay, it's kinetic friction here. So this is a fantastic problem because you know what this problem does? It takes everything we've learned about forces up to this point and puts it into one. So you need free body diagrams. You have two objects, so you have interactions. There's Newton's third law here now, and we know how to deal with friction. So this is a fantastic problem, and let's look at it. Okay, you understand this problem? Pat yourself on the back. Well, don't do that. No, it's not that exciting, I guess. All right. Free body diagram of block A. We have gravity down. Okay, so I indicated F sub GA. Obviously, normal force is upward. I will label it N sub A. Right? The boxes are sliding down the ramp, so there is kinetic friction. There's no static friction to consider here. So the kinetic friction is up the ramp, and then what I have here is an F sub B on A. What that means is that's the force that block B pushes on A. Okay. Now, look at the coefficients of friction here, right? This one's 0.2 and this one's 0.15. Okay, you need the kinetic friction of A to be higher than B. Okay, because B has to be basically more free to move so it can provide a push onto block A. If you match them, then they move down at the same rate. So you could argue that there's technically no contact then. And then, of course, if you make the coefficient of friction for A too low, like lower than 0.15, then they're not in contact at all. A slides down faster than B slides down. So we have to have a coefficient of friction for A that's a bit larger. All right, well, what's going on with B? Well, gravity's huge. Why did I make gravity so big here? Anyway, gravity is huge. Kinetic friction's up the ramp, and then the Newton's third law interaction pair is up the ramp. Okay, I labeled it A on B. And then, of course, normal force is upward. All right, so there's the free body diagrams. And then I'm going to connect here the Newton third law interacting pair. There's only one. It's the contact between the two blocks. All right, so let's write out Newton's second law. So I got a whole thing going on here. Obviously, you can look at the examples, and I was nice, and I did all the math. So anyway, Newton's second law for block A, okay, normal force up, component of gravity down, right? This here is your kinetic frictional force, right? Mu sub K Na. This is the push down the ramp by block B, and this is a component of gravity down the ramp. And I know it's a little hard to see here, but look what I wrote here. Equals minus Ma times A. Okay, what does that mean? Well, look at my diagrams here. X, I labeled X on the right. So the right is positive and the left is negative. So in my Newton's second law equations, I have to indicate that the acceleration is negative. That will not be inherently in your problems. You have to manually put a negative sign if the acceleration is negative. So I have a negative here and I have a negative over here. Okay, notice I have pretty much the exact same equations for B. The y components are completely the same. We have our x components. Now, obviously, the push back is equal opposites, so this is going to be a push up the ramp, so it's positive. Friction is positive, right? Component of gravity, negative, and this is minus MBA. All right, so what are we doing now? Well, now physics is done. Physics is totally done, right? We're doing the math now. So in both equations, you're solving for NA or NB, okay? Then you plug them into the respective places in the x equations. So this equation right here is my x equation with my n sub a plugged in. You want to solve for this FB on A because we know that is equal to the one that's over here. So I'm going to solve for that one. I plug that in over here. And then you got this monster of an equation down here. Okay. What did I do here? Hold on here. Oh, I guess I solved for B on A. And then this whole thing here gets plugged in up there. Then you get this beautiful equation down here, right? Anyway, you got to do some math here. You got to take all your terms with A in it. And there's only one right here. And you move it to the other side. And so you solve for A and you get this monster thing here. We get an acceleration of 1.8. And the problem actually was a kinematic thing. How long does it take the package to reach the bottom? Well, I have my acceleration. We go to the kinematic world, and we say, okay, we have an acceleration, and we know the distance that we're going to travel down the ramp is what, 2 meters? I get 2 meters, right? 2 meters here. So how long does it take to go 2 meters with this acceleration? Well, I solve for delta t, and we get a 1.5 out of that. So this is mathematically a little intense problem here. But these are all really great examples. And again, I'm going to create a discussion thread for this in Canvas. If you want to put questions there, of course, you can always email me questions directly about this stuff. But this is a good lecture. It's a lot of really helpful things I'm showing you here. Let's look at the homework, actually. Okay, so you have these 6 homework problems. Ignore the dates that are here. I will change those because this is something I did last year. But these are all really fantastic problems. They all deal with different aspects of friction here. The first 3 problems or so are really subtle examples of how you deal with static versus kinetic friction. And then when you get down to here, we get more sort of traditional problems. This problem number 6 obviously is really similar to the one I showed you. This problem here is really similar to the one I showed you with the blocks. So the wood block sliding down the wood ramp here. Notice the 27-degree angle here. So it's all kinetic friction stuff here. This one's interesting, actually. This baggage handler problem. So one thing you got to realize about number 4 here is this. You drop the box. Okay, well, the box initially is not moving relative to, well, when you drop the box in the ramp is moving and the box is not moving along with the ramp. So you initially have a bunch of kinetic friction. And the kinetic friction is a little tricky in this problem, actually. The kinetic friction, will exist until the box can basically catch up to the ramp, and then it switches to static friction. So this is a really interesting problem here, but you have to be very careful about how you assign the directions for things. Okay, and all I'll tell you as a hint here is when it comes to the kinetic friction, remember this has to do, kinetic friction points in the direction that opposes the start of motion, that opposes the motion of the object, right? So relative to the ramp, what happens is you drop the box, and the box is moving to the left relative to the ramp. Say the ramp moves to the right. The box is moving to the left relative to the ramp. So you actually have a kinetic frictional force that's actually going to push it to the right. Again, because the motion, if there was no friction, it would just go on to the left. So anyway, this is a little tricky here. A little tricky. All right. In fact, I think number 3 and 4 are very similar in that respect. All right, I think that's all I got to say. Hope everyone stays safe, and I will see you in the next lecture.